Hi guys, welcome back. And for the second part of this lecture, we will focus on representation learning. And exactly, so then how can we infer some information about this from the data about these latent variables? So we start again with our generative model, just as before. And we have the first step, sample from the latent space, and then we generate our data through our generator. We also discussed last time that depending on the form of the generator, if the generator is an stochastic map, then we can generate a density on the data space, right? So then the question is, given this model, and well, yes. So sorry, this was the I just went too quickly. So this was this is a specific example, right? So if we choose our map to be of this form, this is basically a Gaussian reparameterization. Then we get a Gaussian density. The likelihood is going to be a Gaussian density, and this integral is basically going to be an infinite mixture of Gaussians, right? So okay, then all of the stuff that we have said before is that given this generative model, we know, I mean, we have learned how to tweak the theta parameters to fit our generative model to the data. But then the thing is, okay, can we now say something about this latent space, about this latent code? And this goes in the line of representation learning. So this is actually a very old question. The fact of we start with some assumptions about the data, right? In our cases, that we choose a specific kind of prior, and then we use this prior I mean, in our case, to generate data. But after we have seen the data, then in principle we should be able to update or basically our belief about the generative model. And this is a classical question that is famous. I mean, it's so the way to basically invert of how to update this your belief about the latent code is through Bayes' rule. And but this was I think also formalized by Laplace. But even before him, Jacob Bernoulli himself, I mean, he was thinking about this issue of how to invert probability, how to update your belief after you've seen some data. And this is what we will do. So given that we have a density here, in principle, then we could use Bayes' rule to infer what is called the posterior distribution. So it's like the probability of a given latent code given the data. The issue here is that this P of theta here, which is I put theta star to say like once the model has been optimized, and the issue is that this P of theta star is not computable because it comes from this integral, and as soon as we parameterize our likelihood, this P of theta here with a neural network, then we cannot do this integral. That means that this whole rule cannot be directly used. So we have to come up with some ways to update that. Yeah, just a short remark. There is about these three guys. I mean, these three guys here, and the maximum entropy principle. This is a super nice read that I just recommend. All right. So then, what we want is try to get the true posterior distribution after we have seen the data. We cannot compute it, so we want to approximate it. And what we do is that we will introduce what we call a stochastic encoder, which is going to be another function. We call it here Q of phi. And the formalism that I'm going to describe now is is what is called the variational autoencoder formalism. So again, we start with our generative model. And just to start here explaining the figure on the left, then we have the the rectangle here below, this corresponds to that space, and these black points correspond to the empirical data points. This set space is going to be our Latin space. And here, I have this blob here, which represents more or less the center of our prior distribution. So we're assuming that the prior here is a Gaussian, and that's why I drew it like spherically. And all right, so then there is also this map that goes, which is part of our generative model, that goes from the Latin space down to the data space. And now we're saying, so we usually call this term a likelihood. This is again our same generator function. The thing is that in this case, for variational autoencoders, we will choose these maps here to be stochastic. So again, we're using this Gaussian reparameterization. So in that sense, our map will have a support over the whole space. Now here a question, I think I'm blocking it myself, so let me just close this thing for a second. So this is a question, probably this is not the appropriate place where to ask it, but I just thought that it's nice just to think about that, and then we can discuss it later on. Is that, we're adding this, we usually take likelihoods to have this Gaussian noise around, and then you see this thing in many kind of problems, and the question is, why do we use Gaussian noise all over the place for likelihoods, and why does this thing make sense? So we can just think about this thing, and then you can tell me what you think about it. All right, so going back to our problem, we are interested, again, so we want to introduce this approximation to the posterior, and what we do is that we introduce this inference model. So this goes in the other direction. So this is something that goes from the data space, from the empirical data points, and then we will map them with a function. This is going to be a stochastic function to the Latin space. That's what we call it. This is our encoder function. And we will, in this case, or for the moment, we will parameterize it again as a Gaussian. So with these two things in mind, the question is, okay, how can we find the best parameters theta and phi now for the encoder that best describe our data set? And what we do is that we will define these two joint distributions here, right? And with these two joint distributions, we might ask, okay, so we want to put these two guys together because this includes the empirical data set, right? And let's just try to minimize the Kullback library. We can use the Kullback library because in this case, we have densities all over the place. So then this is what we do. So here, this is the definition of the Kullback library. We can expand the log and reorganize terms a bit. We basically take out the term corresponding to the empirical data set. It doesn't have parameters, so it's basically a constant. And then what you see is that this term, we can recognize it immediately as a Kullback library between the prior distribution and our encoder. So this is interesting. This term in between, which is what we actually optimize. This is what is called the variational lower bound of the variational autoencoders. And you see that if we maximize this quantity, then we're effectively minimizing the distance between these two joint distributions that we define. And the whole autoencoder interpretation comes if we look at the different terms of the elbow. So if we look at the first term, what we see, this is basically a reconstruction term. So we're looking at the probability that the point X that comes, that this condition on the set that comes from the posterior is actually in the empirical data set, right? So this is literally a reconstruction cos term, and I draw it here in this blue in the figure. And the second term, we can understand it as a regularization, which basically tries to put together the posterior distribution with the prior distribution. Just as a remark, if we were to actually neglect completely this term, we will basically be back to the standard autoencoder framework. So then let's just take another look at this elbow. I mean, so elbow stands actually for evidence lower bound. And the thing is that, okay, what is the connection with the evidence, right? Why is this a lower bound at all? And because as I decided to derive it was just to show that it comes out as a minimization of this Kullback library between these two joint distributions that we define. So in this case, what we will do is, what I actually want you to do is to show that this elbow that we define here is indeed a lower bound to the evidence or the marginal log likelihood of our generative model. And as a second task, you could also try to show that the Kullback library between these two distributions that we consider. So this is the guy that we wanted to look at. That we started with, and the one that we want to minimize. So we will see that this actually is an upper bound to the distance between the empirical data set and the marginal data set of our generative model. So okay, then with this things in mind, then we can just go to the next immediate question, which is, so we want to maximize this lower bound. We want to maximize this function L, and but there is a problem, right? There is this expectation value with respect to the encoder distribution of some function, right? In our case here is of the likelihood, and well, there is also a term inside the Kullback library. The thing is how to compute this kind of gradients, and we actually ran into this problem before for the GANs. We also had to compute gradients over expectation values of functions, and we didn't talk about that then, but what we're going to say here now also applies in that case. So there's this, there's this reparameterization that we're going to do, and the idea is actually very simple. What we will do is just instead, we will see the samples from our encoder distribution as coming from a reparameterization of our distribution itself. So we will say that there is that the stochastic component of our sampling comes from a fixed distribution, a simple distribution, and then we pass this sample through a parametric function that in our case is a neural network to get the actual sample. This is precisely what we do for GANs, and we are repeating it here. And what we see is that if we take this reparameterization trick into account, we can write the expectation value over some function h as follows, right? So instead of having set, we put there the output of this parametric function, and it's going to be average. It's going to be the expectation over now the simpler distribution, and this follows because the density, if you integrate the density of Q of phi of Z and integrate the density of P of E, both are normalized, so both have to be equal to 1. So with this expectation over the simple distribution, we can actually approximate it as a Monte Carlo sampling, and that means that we can now compute this the gradients of over the expectation values of the function that we want to optimize using this estimator. And this seems to scale. In practice, it's actually like a very good approximation. I put here 2 papers. First, the actual autoencoding paper, and then the contribution presented that actually came about the same time. Both of them introduced the autoencoders and the reparameterization tree. So the difference here with GANs is that with GANs, we didn't really care that much about the density. But if now we are interested in having an encoder distribution that has a specific density, then the transformations that we can make, this f of phi that we can choose, are very particular. So the example that we already know is the reparameterization for a Gaussian. We can write, we can sample from a Gaussian if we write our f of phi function in this way, as a combination of these 2 functions, where mu is the mean, parameterized. This is going to be again a neural network, and then there's some noise that comes from a Gaussian, and then there's sigma, which is going to be the standard deviation. So Another very important example is what happens if we want to sample from a categorical distribution. This is key once we want to train, once we want the latent space to be discrete. And I mean, I cannot emphasize enough how important this reparameterization is. And there were also, in this case, also two papers. This is one of them where they propose this reparameterization for categorical distributions. So yeah, another example in particular that I just put it because I mean, using it currently is for the Weibull distribution. And the thing is that the problem is that there are some densities for which you really cannot do this reparameterization. And a particular example are the gamma variables. And this you usually use when you want, when your variables, your random variable, you want it to be positive and sparse, or and small, close to zero. So there is no good reparameterization, but the Weibull distribution is actually quite similar to it. And what we do in practice is that instead of using the gamma, we use the Weibull. So, okay, this is nice, but the thing is that autoencoders are known for some problems, right? So the things that we know is that if you try to use a variational autoencoder to generate images, then the images look kind of blurry as compared with GANs. And we already should have some intuition about why is this so. The thing is that, you know, so we have already said all of these images, I mean, these image problems, I mean, the empirical distribution has a low D manifold. I mean, these distributions are supported on a low D manifold, and we're trying to fit a Gaussian on top of them. Or I mean, for autoencoders, people try to put Bernoulli distributions also on top of that. And the thing is that, you know, so you cannot really fit properly a density to this low D examples. And so if you put a Gaussian there, then the standard argument is that you are basically averaging over the space, and that's where you get some sort of this blurriness. Another famous problem is that usually, and this is crazy famous for text autoencoders, when you want to generate text, and then you get a sentence, you encode it to some Latin code, and then you go back to the data space, and then you try to regenerate this sentence. And usually, since the decoder in this case is autoregressive, I mean, you please ask me about this thing if you're curious. The issue is that, I mean, the decoder is capable of completely ignoring the Latin code, and some problem that is, I mean, people usually say that is related to this issue of ignoring the Latin code is when you have low mutual information between the data and the code, and people also relate this thing to the question of disentangled representations. But to discuss about disentangled representations, that will be yet another lecture. So let's just keep it here, but let me point out a specific comment that that is, I mean, it's important to keep in mind. So one can show that if you actually look at the elbow, and then you try to I mean, so you compute the expectation with respect to the data, which is what we do. You can show that the elbow is actually equivalent to this term, where the last quantity is the mutual information between the data and the Latin code. But here there is a difference. Now the Kullback-Leibler term is not between the prior and the encoder, but is between the prior and some new quantity that I'm defining here below, and which we call the aggregate posterior. And it's basically the expectation value of the encoder under the data. The problem is that, I mean, as we said before, so not only the posterior is complicated because we can put there a neural network and so on and so forth, but now we also have to integrate over the unknown empirical distribution. So this is in practice intractable. But in any case, people consider, instead of the elbow, what they do is that they consider this, let's just call it loss prime, which is basically the elbow plus the mutual information. And what they do is that they try to maximize this new quantity, and then in principle, if you consider this loss instead, you are not only maximizing the likelihood of the data, but you're also maximizing the mutual information between data and code. So the problem here in any case is in practice how to compute this specific callback library, since the density for this distribution is intractable. Well, the nice thing is that we can, in any case, although we cannot get the density, we can sample from it, right? Because if you imagine this expectation value, you can get samples from the actual distribution Q of phi of Z using ancestral sampling, which basically means sample from the data and pass it through the posterior. What you get is going to be a sample from the aggregate posterior. And since we know how to sample from it, then and the prior here is something that we know, so we also know how to sample from it. Then we can compute this distance using adversarial methods, right? We can like all of the stuff that we discussed before, like the variational representation for the callback library. We can use it here to compute this specific distance. And people have done this thing already. And these are just a couple of famous examples. These guys, they precisely do that. And and these last two, they are actually trying to solve the problem with the ignoring the Latin code for text autoencoders. All right. Then, so yes, we saw how to get the autoencoder, the variational autoencoder formalism. And what we said there is that we're trying to put together these joint distributions that we define, basically the generative model distribution and the inference model distribution. We put them together using the callback library. So another thing that one can do, as we did with the GAN, is to consider instead the Wasserstein distance, right? So we again write the distance. In this case is slightly more general than before, because in the case we discussed before, we were looking at the Wasserstein 1 distance. So here, and just we call when the cost here is just any cost function that goes from our data space to the reals, then this is called the optimal transport distance. So yeah, this is again the node. And then what we're going to do, so let's just consider again the same picture of before, right? And in this case now, so P of Z is again the prior of the generative model. G of theta is going to be our generator. And Q of 5 here, this you will see in a second, but this is going to be again the aggregate posterior. And F of phi is just the function, so basically our encoder function that goes from data space to latent space. So I'm not explicitly writing them as densities to emphasize that we can use for the Wasserstein autoencoder, we can use maps that are fully deterministic. And okay, so then the trick to get this is actually, it's in this paper, the Wasserstein autoencoder paper, is a nice idea. And the main thing is that, remember these couplings that we were talking before? So these guys here, which are the ones that we want to, the one that we want to maximize. What we say is that we just parametrize them in this specific form. So it's basically a map that goes from data to some function which suspiciously looks like an encoder, and then goes down again to the data. So we can imagine this blue path as the kind of paths that these couplings do. So we basically are going from the empirical data set that is in data space up to some latent space and then down again, like an autoencoder. But you know, like this, so we know that these couplings, they have to be, the marginals have to go one to the empirical and one to the generated distribution, so we can check that. And the first one is that if we integrate out that function with respect to y, so with respect to this term, this integral, this term will, there is no more y here, so this will just be 1 because it is a normalized density. Then we get the integral over a set of this term, which is also y, because it's also 1 because it's again a normalized density, and then we get, as we want, the empirical data set. We can repeat on the other side, so this is fine. So we can repeat on the other side, but here, instead, we have a problem. We get this term here, which, as we said before, this is the definition of an aggregate posterior. But this whole term should, in principle, I mean, by definition, it should be equal to the marginal likelihood of our model, right? So then this is only going to be true if we enforce this aggregate posterior to be equal to the prior, because of course, if this guy here were to be the prior, then you see that we get by, I mean, our definition of our generative model, basically, yeah, the marginal likelihood. So if we enforce that, then we can actually write the following distance. So let's just replace here our couplings into our original equation, and it basically boils down to this term, the first term here, and the constraint to have the aggregate posterior equal to the prior, we added by hand. So we will add a regularizer. So lambda is there some term that we need to fix, and then if only when this regularizer is fully I mean, so once this constraint here is fulfilled, then we are really getting this optimal transport distance. So where again, exactly this term here is the aggregate posterior, and we know that, so this we cannot compute explicitly. We have to do it using the some sort of adversarial approach. And well, the first term here, if what we see here, this is just any cause, and this will play the role of a reconstruction. And the only difference is that here, I mean, we can literally use any cause that we're interested in. And the nice thing is that if we choose, for example, the norm 2 as the cause, then the whole Wasserstein autoencoder just maps to the adversarial autoencoder that we mentioned before. So this is like the theory behind the adversarial autoencoder, which is a paper that came before this one. And an interesting comment is that in any case, this distance that we are defining is not precisely equal to the optimal transport distance, but it is going to be an upper bound simply by the fact that we are, instead of finding the infimum over all of the possible couplings, we are only choosing to find the minimum under all of the parametrized couplings that we are introducing. So I think I don't have that much time left, and I wanted just to show you some examples. We can discuss this, I mean, the other ones later on. So the first one was just, so this is an example of the adversarial autoencoders. They wanted to study, like, for example, MNIPs, and they have, their generative model has two latent variables, one continuous and one discrete. And what we see here is that they, so in this direction, we just change the continuous variable that somehow encodes the style. And in the C is a discrete variable that basically labels the number. So this is an example of this disentangled representations. We can also see here, in this case, this was unsupervised discovery of dynamic regimes. So the latent code here was just a discrete variable. And what we wanted to find, just as a simple example here, was just we have a sine function and we want to find the two different frequencies. And by encoding, so this is fully unsupervised, we really don't know which part of the data has which frequency, so we want just to learn it from the data. And one can do that using autoencoders. So the thing is here that the labels, all of the codes, they are time dependent. Another super nice example is this. So let me just hide this thing down. Where the data is basically generated by this. So they simulate some pendulum, and then the position, I mean the angle of the pendulum, they can just they generate images of it, and this is going to be the input that they want to analyze, and the latent code is able to infer this equation. But unfortunately, I don't have really time to discuss this thing. I will just leave it to the question answering session. Also, the last example that I really wanted to mention was about the text autoencoders. So yeah, we will discuss this thing in the question answering. I hope to see you there. I hope that you guys have fun. And yeah, so thanks very much for your attention. And sorry for the extra 5 minutes that I took. And well, I hope to talk to you soon. And yeah, thanks very much.